So this question 31 from DC electricity assignment. The photograph shows a type of a fish which is called an electric ray. Electric ray can produce electric discharge to stun their prey. The parts of a ray body act as a cell in a battery, and in a ray living in a fresh water, the cells are actually arranged in series. But if a ray is in a salt water, the cells are arranged in parallel. The arrangement in a ray can be investigated by comparing a circuit containing 5 cells in series and 5 cells in parallel. Each arrangement of cells is connected across range of range of loads, load resistance, and the current and terminal potential are measured as shown. The results for a current are shown in the table. You can see when the external load resistance is 0.1, external resistance 1, and then 10. The current in series and the current in parallel. It has been suggested that cells are in series for a ray living in a fresh water because the fresh water is a poorer conductor of electricity than salt water. Discuss whether the result support this suggestion. So you can see like they already mentioned when it is in a fresh water, the cells appear to be connected in series. When it is in a salt water, it appears that the cells are connected in parallel. So we have to like suggested that cells are connected in series for a ray living in a fresh water because the fresh water is a poor conductor. Fresh water does not like contain few ions or charges. So in a fresh water, as they are connected in series, so what we can say like for a when the resistance is low because the current should be high. Here in series, when a load resistance is 0.1 here, and this load resistance is 0.1. What was the current? 2.7 and 7.2. When the load resistance is 1, the current is 2 ampere and 1.3. And when the load resistance is 10, the current is 0.55 and 0.14. So in a fresh water, because the fresh water does not conduct electricity good. So if it is so for a low resistance, the parallel arrangement has a high current, you can see. And opposite is there. For a high resistance, the series is having for high resistance, the series arrangement has a high current. So when we compare, the first point is comparing the table. When the resistance is low, the parallel is having a high current. When the resistance is high, the series is having a high current. That is one mark for comparing them. The second thing, so it means the high resistance, which water will be like example, because in fresh water should have a high resistance because fresh water has less amount of dissolved impurities or salt. So as a result, we can say that the high resistance is equivalent to the fresh water. So high resistance is there for fresh water and low resistance is there for. So simply we can say like low resistance is equivalent to salt water, and so parallel is used for salt water and series is used for the fresh water. So for a fresh water, it use series, and for salt, because they mention in the beginning, like arrangement of a cell can be series, can be parallel for a ray, electric ray. And in a fresh water, because the fresh water, which condition, like in a fresh water will have a high resistance. So fresh water is having a high resistance. So we want more current. So that's why, or the fish to produce more current, it should appear that the cells are connected in series. But in a salt water, what happens? The salt water having a low resistance. So when it is having a low resistance, the current is high. So it means in a salt water, the combination of the cells are like parallel for this electric ray. Is it clear this part? The comparison? The next, calculate the internal resistance of one cell using the following results for 5 cells in series. The load resistance is 2.5, the terminal potential is 3.3, and the current is 1.5. The EMF of the 5 cells together is 6.9. So we have 5 cells which are connected in series. And we have to calculate internal resistance R. This combined is equals to 6.9 volts. There is a load resistance that is 2.2. And the current is equals to 1.5. So current 1.5. So current of 1.5 ampere will flow through each of them. And we need the internal resistance. So what we'll do, like first we'll find, because each cell is actually having an internal resistance, like there will be, if I want to draw, this is internal resistance for 5 of them. So if I need for one, I will simply divide it by, after getting the internal resistance of 5, I will just simply, the last answer I'll divide by 5, so I'll get for 1. So we use the formula that EMF is equals to voltage drop internally, which is IR. So this is I into 5R because each is having resistance R. So 5 cells, they will have 5R plus V. And V is equals to IR also. So in place of V, I can also write I and capital R, which is external resistance. Now we substitute the value, the EMF, the total EMF of the 5 cells 6.9. The current, that is 1.5 into 5R, plus the current is 1.5 into the load resistance, which is 2.2. So this is equal to 1.5 into 2.2, 3.3. It will move other side. So this is 6.9 is equals to 1.5 into 5R plus 3.3. It will move other side. So 6.9 minus 3.3 is equals to 1.5 into 5R. Then this or is multiplied like this will be 2.4. 2.4 divided by 1.5 and then divided by so the final, when we solve this to 6.9 is there minus 3.3, which is 3.6, and 3.6 divided by 1.5 is 2.4. So when we simplify this, all is 2.4. So 2.4 is 5R. So if we need R, it will be 2.4 divided by 5. That is equals to 0.48 ohm. So internal resistance of each cell is equals to 0.48 ohm. Explain why the voltmeter should only be connected directly across the load resistor if the ammeter has a negligible internal resistance, negligible resistance. So whenever we are measuring, so what will happen? The question is why the voltmeter should only be connected directly across a load resistor if the ammeter has a negligible resistance. Like here, The circuit, the CE circuit, you can see. So why we should connect a voltmeter in this region? Why not parallel to this? Like here, this is a load resistance. So why the voltmeter should be connected in parallel to the load resistor when the resistance of ammeter is negligible? That is the main question. So what actually happened? Because if ammeter, like as ammeter and variable like fixed resistors are connected in series, so the voltage will divide between them. And as you can see the previous one, so why the voltmeter should only be connected directly across a load resistor if ammeter has negligible resistance. So if and this one, if ammeter was having a considerable resistance, what might happen? That some of the voltage, like if we ignore the resistance of ammeter, then we can connect a voltmeter in parallel to load resistance. Otherwise, we should all connect in parallel to both ammeter and the fixed resistor. Because what will happen? Say this is how many cells? Five cells are one, two, three, four, five cells are there, and say this was 6.9. So if this was 6.9, some voltage will, if ammeter was having a considerable resistance, so some voltage will drop across ammeter and some voltage will drop across the fixed resistor. And that's why we connect a voltmeter in this manner. But if the voltmeter, if ammeter was having a negligible resistance, like if resistance is negligible, so there will be almost no voltage drop. Practically there will be some voltage, but if we say it's negligible resistance, so there will be no voltage across ammeter. In that case, we can connect a voltmeter in parallel to the load resistance, and the voltage of the load resistance will be same as the voltage across the voltmeter. So if it is having a considerable resistance, we have to connect this voltmeter parallel to this series combination of ammeter and load resistance. If negligible resistance, we can simply connect parallel to a load resistance as there is no voltage drop across the ammeter. Is it clear, this part? Then the next one, in an experiment to determine the resistivity of a salt water, a plastic container is filled with a salt water. A piece of a metal foil are placed inside a container and covering the ends. The resistance meter is attached to a piece of a metal foil and used to measure the resistance between X and Y. Resistance of a salt water is 1.2 kilo. Calculate the resistivity of the salt water. The formula which relate the resistance and resistivity with length and area R is equals to rho L by A. If we need the resistivity is the subject, so it will be RA divided by L is equals to rho. So we have the resistance here, which is 1.2 kilo, which is 1200. So we can say 1.2 into 10 to the power 3. Area of cross section, because so this will be 5 into 3, but it is in centimeter. You should convert into meter and then multiply, or you can get area in centimeter square and then convert into meter square. Both ways it is correct. So 3 centimeter will be 0.03 meter times 5 centimeter 0.05. This will be the cross sectional area, and the length from one end to another, the length is 13 centimeter. So 13 centimeter, that is 0.13 5 meter. So when we divide directly, we'll get the resistivity, which is 13.3 and the unit of the resistivity is ohm meter. So frequently you will use this formula to solve questions related to either resistance, resistivity, sometime area you have to find, or sometime length. When a ray is stunning its prey, it produces a potential of 45 volts and the current of 0.12 in a burst of duration of 5 milliseconds. And there can be up to like 400 bursts in an attack. Calculate the energy transferred by the ray in 400 bursts. So first we'll find how much energy is transferred in one burst and then multiply by 400. Electrical energy is the product of power and time, or power is the product of voltage and current. So we can say VIT. So voltage is 45, the current is 0.12, and the time is in milliseconds. So you have to convert into seconds. So it is 5 milli, means you have to divide by 1000, or you can say 5 exponent minus 3. This will be the energy for one burst. But because there are 400 bursts, so we'll multiply the total with 400. So that is about 10.8 joules of energy this ray will transfer in 400 bursts to its prey. The current and the potential difference voltage are there. The graph shows it's produced from the result. So whenever, remember, this is a VI graph or IV graph for a battery with internal resistance. So whenever the y-intercept is there, this y-intercept, what it represent? It will represent the EMF. And what the gradient will represent? Gradient represent the negative of the internal resistance. Or you can also say opposite, you can say like negative gradient will be equal to internal resistance. So it's the same thing. So EMF, what it is represented by? It is represented by the y-intercept. And the internal resistance is a negative gradient. That's why option B will be the right answer. Which of the following is equivalent to a single base unit? So coulomb per second, which is current, and current is a base unit. Current is basically a base quantity, and ampere will be the base unit. So that's why A is the right answer. What about the second one? Joules per coulomb. Joules per coulomb is actually equal to voltage or volts. That is not the base, that's a derived quantity, or the unit will be derived. Joules per second. So joules per second is actually power or watt. That's again, it's a derived unit. Meter per second, it's a unit for the speed. That's also, it gives a derived unit. It's a derived unit, and even for a derived quantity, which is speed or velocity. So A is the right answer for this. In question 34, the current in the wire is I and the drift velocity of electron is V. The wire is replaced by another one, same metal but half a diameter. If the current in the new wire is same, the drift velocity is, so first we have one wire in which the current is I, the drift velocity is V. The wire is now replaced by another one which is having a half diameter, but it has, they mentioned they have the same current. We have like here drift velocity is V1, this drift velocity is V2. What is the relation between the diameter and the area of the cross section? Area is equals to pi r square, or you can say area is equals to pi d square by 4. These are the formulas for finding the area of cross section of a wire. So what happens if the diameter is divided by 2? It vary with the square, so area will divide by 4. If a diameter is divided by 2, area will divide by 4. And because two wires are made from same material, so I can say the current, if I say this is sample A and this is sample B, The current in sample A is same as current in sample B. And current according to transport equation is equals to N A V Q. And this will be N A V Q. Now, how we can relate? Like if I say this velocity is VA, this velocity is VB. NV, because they mention it's of same material. So when there are same metals or same material, the charge carrier number of the charge density or charge density is the same for both. So we cancel out. If area of this wire, I'm saying A, what about area of the second wire? It will be A by 4. Because we halve the diameter, so area will decrease by 4. So this area is A, this area won't be A, this will be A by 4. And Q also cancel with Q, it's the same thing. So Q is same, that is cancelled. So here I can say A into drift velocity in sample A is equals to A by 4 into drift velocity in sample B. When I simplify, A will also cancel with A. So this 4 is, we want, the question is if the current in the new wire is same, the drift velocity is like, what is the drift velocity in the second sample? So this 4 is divided, other side will be multiplied. So drift velocity will be 4 times compared to the first one. Like in the second sample, the drift velocity will be 4 times. That's why option D will be the right answer. So if we keep all the parameters same, what is the relation between the current and what is the relation between the drift velocity and area? They're inverse. So, and you can also do it by this way, like A is equals to N A V Q. We don't want to change I. I is equals to N A Q V. We don't want to change this I. The drift, this cannot be changed for a metal, this cannot be changed. So what happened when we decrease the, like, so if we want to keep the same current in both of them, so I is equals to N A V Q. N is not changing, Q is not changing. So what happened? If we reduce the diameter by 2, area will decrease by 4 because area of cross section is pi d square by 4. If diameter is half, the area will vary with the square, so it will decrease by 4. If the area decreased by 4, to keep the same current, the drift speed should increase by 4. So that's why 4D.